In the last video, we explained how you could have things like phosphorus pentachloride, which are difficult to draw using just normal conventional covalent bonds. We're going to look at some more examples of that. So we're going to start off by drawing xenon tetrafluoride. So, like always, start off with Lewis dot notations for all the different elements involved. So there's xenon, which is 8 electrons. It's got a full octet, so there are no bonding sites available to bond with the fluorines. But because fluorine is so highly electronegative, it's so attracted to electrons that if it can't share, it will steal. Is even strong enough to steal from most noble gases. You can actually make compounds involving fluorine, involving argon or krypton or xenon. It's not strong enough to steal from neon or helium. Neon's going to basically have a greater nuclear charge than fluorine and same energy level, so it's actually holding onto its electrons stronger than what fluorine could. But for the ones at the higher energy levels, it's strong enough to do this. So what we're going to do is to make it bond is that we're going to steal one of these electrons. So that's now fluorine minus, that's now xenon plus, and the other one can share. And if I clean it up, it's going to just look like this. And again, I would call this type of bonding partially ionic, partially covalent, though it would be acceptable to also write it like this. Because you are just saying, well, since these bonds are partially covalent, I'm just going to represent them as covalent bonds. So there's two covalent bonds. Though I'm really disturbed by this because it makes it look like xenon has 10 valence electrons, which does break the octet rule and would involve d orbitals, which are actually not in play. So next up is sulfur dioxide. So I'm going to start off with the electron dot notations for sulfur and for oxygen. I could easily covalent bond here because there's an available bonding site. And let me go ahead and do that again. And at this point, there are no available bonding sites for oxygen. But since oxygen is high electronegative, more so than sulfur, if it can't share, it will do the next best thing, which is steal. So if oxygen steals one of those electrons, then it can share with the other one. So this is where oxygen is different from something like fluorine or chlorine. Oxygen, one oxygen atom, can both steal and share electrons. When you're looking at chlorine or fluorine, something like that, when you or do this, you are always adding pairs. So one is stealing and one is sharing. Let me go ahead and just clean this thing up a little bit. So here is the cleaned up version of it. Since oxygen stole an electron, it's going to have a negative charge. Sulfur lost one, giving a positive charge. Overall, there's no charge. That is the structure of sulfur dioxide. Now, it would be acceptable to write it like this. That's basically representing all the bonds as covalent bonds. So the ionic bond between this oxygen negative charge and this sulfur positive charge is just represented as a covalent bond. And you get something like this. It's probably the most common version. If you look up sulfur dioxide, you probably mostly look like this, but sometimes you'll see this version as well. Advantages, well, that's kind of easy to draw, maybe a little bit more common, written this way. And you don't have as many charges floating around. But sulfur does have to violate the octet rule, and how that can be explained does not make any sense to me. So I would end up preferring this. If you draw it like this, I'm assuming you're pretending like everything is covalent, even though it's not all 100% covalent. Now, we had drawn a few polyatomic ions before. So let's look at ones like ClO2 minus, which is one that is called chlorite. So to draw that, I'm going to start off with the electron dot notation for these elements. I'm drawing it with chlorine in the center because really electronegative elements like oxygen usually end up combining with less electronegative elements. If they bond with something that is equal to their strength, they don't get much electrons that way. If they bond with something weaker, then even though they're sharing electrons, they're shared more toward the oxygen side, and so it's favored to go to the side that has more electronegativity. There are some compounds that have oxygens bonded to each other. Those are highly reactive compounds. So if I do some sharing, one more thing. This is chlorite, it's an ion. It's got a negative charge, which means it's an extra electron. Where should the extra electron go? It should go to the most electronegative atom, in this case, oxygen, making that oxygen O minus. After this, I'll just do the easy stuff to do. The easy bonds to do would be to create one between that just by sharing the pair of electrons. To get this oxygen to bond, I would have to steal an electron from chlorine, and that can happen because oxygen's more electronegative than chlorine, making that O minus. Chlorine now has a positive charge, and then they can share. And here is the cleaned up version. Both the oxygens are O minus, chlorine is Cl plus, though it would be acceptable to represent all the bonds as covalent bonds, in which case this ionic bond between oxygen and chlorine would be represented as just an extra covalent bond, making it a double bond. Hey, advantage, less charges. Disadvantage, breaking the octet rule with chlorine. Now, to make things like ClO3 minus, which is chlorate, or ClO4 minus, which is perchlorate, what would have to happen is each extra oxygen would steal an electron and share, and steal and share. So you can make these two just by continuing the same sort of process that you did to put in the second oxygen. Also, for sulfur dioxide, you could make sulfur trioxide just by doing another stealing and share. And for xenon difluoride, you could certainly make xenon tetrafluoride by bringing another two fluorines, one to steal and the other one to share. So this does really increase the number of possible compounds that you form, and this is actually not very unusual, especially considering that some of these polyatomic ions are really, really common chemicals that you run into. I hope these examples help with representing these slightly more complicated compounds or ions. Thanks.